Okay, so let's talk about what waves are. Okay, waves are just oh, by the way, everybody who's listening to this, possibly in the future, I sound like I've been smoking for 45 years because I have a cold. So you're just going to have to live with it. Yes. Okay, ready? Let's do this. Okay, so waves. Waves are a way of transferring energy from one position to another. There's two kinds of waves. These are transverse waves, which are up-down waves. So in other words, if you're sitting in a transverse wave, you're bobbing up and down and up and down and up and down. A longitudinal wave, oh my gosh, this is a terrible way to draw it, but I'm doing my best I can. Okay, it's like where things get compressed and then spread out. Okay, so if you've ever been in an audience and everybody rushes the stage, you have felt the experience of a longitudinal wave moving through you, like compression, and then everybody's like, wait, what are we doing? And then you feel the relaxation. So that's what a longitudinal wave would feel like. Okay. So that is what waves are. Okay, energy is moving from one position to another. Let's talk about, this is the most common type we talk about in here. And that's because when we deal with electromagnetic waves, we're dealing with transverse waves. A couple things that are important. Okay, if the thing was not wiggling, it would be pretty flat, right? Like, it wouldn't be moving. So that is that what we call like the equilibrium line. The amplitude is how high this is, okay? The way your ears experience this is loudness. Okay, so the height of the wave. All right, from one position, from peak to peak is one wavelength, and we use this little symbol to show wavelength. That's called a lambda, and the way you can remember that is you draw this. See the shape there? Okay. And then somebody usually goes, what's that? And I go, it's a lamb, duh. These are the things you learn when you lecture. By the way, I have a student here with me. Say hi. Hello. Okay, so that's that. All right, so wavelength, the longer the wavelength, the lower the sound. So my voice currently is making, sorry, it was Chewbacca / music time here on Fridays at school. So my voice is currently making waves that have a longer wavelength, so they're further between peaks because I'm sick. Another way that is related to that is frequency. So frequency is how many of these ups you have every second. So boop, 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 how many of those, okay? So somebody, high frequency voice, I cannot make that sound like a ee, okay? So the low frequency sound is like, okay? So low frequency, high frequency, they're related by this equation. If we're talking about light, so the velocity, or if we're talking about any kind of wave, the velocity is equal to F lambda. So these guys are inverse to each other. So if the frequency gets higher, or if the frequency gets bigger, the wavelength will get lower. If the wavelength gets longer, the frequency goes down. Okay? You often see it written like this: C is equal to F lambda. That's the same thing, it's just referring to light. That C is 3 times 10 to the 8th meters per second. That's how fast light is going. Good? Okay, so now let's talk about index of refraction. Okay, so this C, the speed of light, this 3 times 10 to the 8th meters per second, that's the value in a vacuum. In other words, where nothing gets in the way of the light. But in other things, it might slow down. In fact, there's a place, I think, somewhere in the world where they made a little tube where they could put light in one end, and it moves so slowly they could like go out for a cup of coffee and come back, and light would just be reaching the other end, which is cool. You don't need anything fancy, though, to slow down light. Glass will do it, okay? So I think glass is about, or I'll explain. So in different materials, light moves at different speeds, Okay. One thing we kind of use to talk about what would slow light down the most is the index of refraction. Okay. So a vacuum is basically 1. I think air is like 1.003. Glass is like 1.5. And then there's stuff that's even more dense and slows it down. It'd be like 2.2. Okay, so there's all these values out there in the world, and you could look it up. You could be like, hey, how much would this sapphire that I found, how much would this slow down light? You could look up its index of refraction. The bigger the index of refraction, the slower the light is going to go in there. And you're like, why in the world would I care about that? and you should look that up, because there's a couple equations that go with that, but I won't go into right now. Like, how much is it going to slow the light down? Well, why does that matter? Okay, so it matters when you go from one material to the other, and you are not going to go in at a straight line. This is the normal line, in other words, the perpendicular line to the surface. Okay, so let's imagine that we had a beam of light coming in at an angle of, like, let's say 30 degrees. Okay, that we would call our angle of incidence. Notice that you are measuring from the normal line to where the light is hitting. The number one mistake is they'll often give you the problem, and the jerks will be like, ooh, it's going to hit at this angle from the surface, and then you'll plug that in the problem and you'll cry for like 3 days because you won't know why your math is wrong. So always remember you're measuring from the normal line. Let's get rid of this evil thing here. Okay. So what happens is the light's coming in, and imagine yourself sort of driving a car, okay, and you're going really fast, and you're gonna hit really thick grass, okay, with your car. So you're driving this way, you're gonna hit the grass. This wheel hits first. So what's gonna happen to your car? Yeah, it's gonna move, but this tire slows down before this tire. So your car is gonna jerk kind of like this. And draw that very well. So, boop, and then, oh, I really didn't draw that well. It's more like, you see it?
Yeah, I was kind of gonna go say like it's going to like almost like reflect, but then I was like I didn't know how to.
Yeah.
I'm a writer. I don't.
It's okay. We call it refraction. Okay, so in other words, you had one path and you're going to get bent the other direction. Okay, so this is turning into a mess. Let's make a new sheet. Okay, so we got a few things here. So this is the light coming in, so this is our angle of incidence. The light gets bent, and this is our angle of refraction. I can tell just by looking that this material is denser and has a slower or a higher index of refraction than this one. How can I tell? This angle is smaller than this one. When you go from something with a lower index of refraction that's like a little bit less dense, the angle is bigger. When it gets squished into something that's going a little slower, the angle becomes smaller. It's not scientifically accurate, but I like to think of it as though out here in the free air, everything was like more relaxed, so the angle like stretches out. And then when it comes into the more dense material, it gets squished inward. So just by telling, like if you looked at this guy here, I'll show you. Okay, let's say we had like this, and then it was like boop. Okay, and this is your normal line. Okay, which one has the lower index of refraction, the top or the bottom?
Or top.
The top, right? Because it's a big angle, small angle. Here, you can do it with this guy. I can make these up. So let's say there's like some material here, and then there was like another material here. We could compare these. So here comes, let's do this. So like, boop, and then boop, and then boop. Okay, let's go through these. Okay, we'll call this area A, we'll call this B, we'll call this C. Okay, comparing A and B, which one has the lower index of refraction?
B. A.
Okay, good. Yeah, because there's a big angle and then it goes into a small angle. So now we'll go down and we'll compare these two. Okay, so now this is your angle of incident and this is your angle of refraction. Which one has the lower index of refraction, C or B?
C.
Okay, good. Okay, so let's say that you shone a flashlight into water. Okay, now water I think has, off the top of my sick little head here, I think it has an index of refraction of 1.33. And air up here is like really close to 1. Okay, close enough. My question is, what will happen when the light hits the water? Okay, so first thoughts. Okay, big angle here. We're going into something that has a higher index of refraction. So what are you sort of expecting the angle to be? Bigger or smaller than 50 degrees when it gets in there?
Small.
Yes, good. So we would draw something that has a smaller angle. Okay. Let's actually calculate that now using something called Snell's law, which is the most adorable name for a law ever. Snell's law. Okay.
Not gonna lie, when I read that name, I was like, that is the funniest name in the world.
Isn't it cute? I want a dog named Snell. Okay. All right. Now it looks so scary, but it's really easy. Nothing to be scared of. Snell's law. Okay. And we have equations in here that people should be afraid of, but it's a little bit like Bernoulli, where it looks scary, but it's like super easy once you get the hang of it. So N1 would be your angle, whatever it's moving through originally. The index of refraction is moving through it, so 1. Sine, and then the angle is 50 degrees, because that's our angle of incidence. And remember to measure always from the normal line, always from the normal line. Okay, equals, N2 is 1.33 sine theta 2. Okay, I'm running out of room here, and I'm also teaching on an angle. So what are we going to do to solve this? You're going to take sine of 50 divided by 1.33.
Like for these.
Important. Make sure your calculator is in degrees. Oh my gosh, I just misspelled degrees. Not radians. Oh my gosh, radians, not radians. Degrees, not radians. Very important. So important, I got out my special effects budget for this video. Okay, there we go. Good? Nice. All right, so my student here was kind enough to throw that in her calculator. You got 5, 7, 5. Oh gosh, it keeps going. 9. Okay, I wouldn't even write this down if I was you. Sine of theta 2. The reason I wouldn't write it down is I'd immediately just take the inverse sine in my calculator. So let's do that and let's find out what angle we get. So go ahead. And we get 35 degrees. And we just take a little, reality check. Is it smaller than the incident as we would expect? And it is. And we sing happy songs and we feel like geniuses for 30 seconds before AP Physics senses happiness and comes back for our souls. Dun dun dun.